Okay, today we will move on to linear models and estimation by least squares part 2. Chapter 11.4 is properties of the least square estimations for a simple linear regression case. The first one we'd like to prove is unbiasedness. So what we want to show is that our estimators, beta 0 hat and beta 1 hat, they are unbiased. What it means is expected value of beta 0 hat is same as beta 0 and expected value of beta 1 hat is same as the true beta 1. So we want to check whether our estimator have this unbiasedness property. So what is our estimators? Our estimators are this, and we would like to check this equation. So to do that, the random part of here is y, related y. So let's try to check whether what is expected value of beta 1 hat, and this is expected value of SXX, which is sum of xi minus x bar, and they are not non-random value, so non-random thing. And here this part is sum of xi minus x bar times yi minus y bar. Okay, and here the expectation can go inside, so the random parts are only here. So the expectation goes inside here. So this is expected value of, oh no, so this is sum of xi minus x bar square. This is constant part, and this is also constant part, and the expectation goes to here. The expected value of yi minus y bar. Okay, so here what we would like to check is what is expected value of yi and what is expected value of y bar. So that's what we need to know, and what we know is that yi is beta 0 hat. Actually in reality beta 0 plus beta 1 xi plus epsilon I. That's the true situation. So expected value of yi is this part is known part, and expected value of epsilon I, this is 0. So expected value of yi is beta 0 plus beta 1 xi. And what is expected value of y bar? And this is again this is expected value of sum of xi divided by n, and so this is expected value of each of xi's, and so this is sum of expected value of xi's divided by n, and this is and sum of beta 0 plus beta 1 xi, and this is we have n beta zeros, and divide by n, which is beta 0, and plus beta 1 sum of xi divided by n, which is beta 1 sum of xi divided by n, which is x bar. Okay, so expected value of y bar is this thing, and so let's put this here. So from here the result is sum of xi minus x bar squared. Here sum of xi minus x bar, and here expected value of yi is beta 0 plus beta 1 xi, and minus expected value of y bar, which is beta 0 minus beta 1 x bar. Okay, and so the result is we can cancel beta 0, and result is sum of xi minus x bar squared, sum of xi minus x bar, and we have beta 1 xi minus x bar, this thing. And actually this is you can move this beta 1 outside, and that is beta 1 times sum of xi minus x bar squared, and here sum of xi minus x bar squared. And so these part cancelled, and you will going to have beta 1. So we showed that expected value of beta 1 hat is same as beta 1. And what about expected value of beta 0 hat? And for here, this is expected value of y bar minus beta 1 hat x bar. And expected value of beta 1 hat is beta. And so here a here random part is this one and this one, and expected value of y bar minus expected value of beta 1 hat is beta from the previous calculation, beta 1 x bar. And so from here expected value of y bar is here, so actually this is beta 1 x bar, and so this is beta 0 plus beta 1 x bar minus beta 1 x bar. So this part cancelled, and you will have beta 0. And so we showed unbiasedness property. Okay. Next, let's derive the variance of beta 1 hat. And actually the variance of beta 1 hat is this thing, and let's derive this. So what is beta 1 hat? Beta 1 hat is sxx, and here sxy, and this is sxx, and sxy is sum of sigma xi minus x bar, and yi minus y bar. And the random part is here, and also this part is not necessary. So actually if you check this numerator, xi minus x bar, yi minus y bar, and this part becomes sum of xi minus x bar yi, and minus sum of xi minus x bar y bar. Okay, and actually this part is 0. This part becomes 0 because this part is sum of xi y bar minus plus n times x bar y bar. And here this thing, sum of xi, this is n times x bar. So these two parts can be cancelled, and so this one is same as this one. So we can express beta 1 hat as sxx, here sum of xi minus x bar times yi. Okay, and let's calculate uh, variance of beta 1 hat, and this is variance of sxx, uh, sum of xi minus x bar yi. And here, um, uh, this one, here, these are constant, and so this thing becomes sxx sum of xi minus x bar squared and variance of yi. And here, variance of yi, this is variance of beta 0 plus beta 1 xi plus epsilon. And this part is constant, and variance of epsilon, this is sigma square. So variance of yi is sigma square. And so, oh, actually this one is squared. So variance of this constant and this go out with square term. So this is equivalent to sxx square, and this thing is actually sxx, and variance of yi is sigma square, and so 1 of sx cancelled, and the result is sxx here sigma square. So we derived this thing. Okay. Let's derive the variance of beta 0 hat. So variance of beta 0 hat, this is variance of beta 0 hat is y bar minus beta 1 hat x bar. Okay, so this thing, and actually this thing is variance of y bar plus x bar square variance of beta 1 hat minus 2 times x bar covariance of y bar and beta 1 hat. Okay, so in this part we need to calculate these three variances, and for variance of y bar, this is actually variance of beta 0 plus beta 1 x bar plus epsilon bar, and actually this part is constant, and so variance of epsilon bar, that is n sigma square over n. So this is calculated, and also we also derived the variance of beta 1 hat. So the left thing is to calculate covariance of y bar and beta 1 hat. And so let's check what it is. This is covariance of y bar and beta 1 hat. This is covariance of 1 over n sum of yi and sxx sum of xi minus x bar and yi. Okay. Yeah, this is it, and this is actually sum of I equals to n, sum of j equals 1 to n, covariance of n over yi, comma sxx, sum of no, not sum of, so this is xj minus x bar yj. And for this covariance, if I equals j, then covariance of this thing becomes n times sxx xj minus x bar and sigma square. The covariance of this thing is this one for if I equals j, and if I is not equal to j, then the covariance of yi and yj, this is 0. So this part becomes I equals 1 to n, and n over sxx and xi minus x bar times sigma square. Okay. And actually this one is constant, and if you, so actually here sum of I equals to 1 to n xi minus x bar, actually this is 0, because this is sum of xi minus n x bar, and actually this is n x bar, so these two cancelled and this is 0, so this is 0, so this part is 0, and so this one is 0, and this one is sigma square over n, and this one is sigma square over sxx. And so as a result, the variance of beta 0 hat, this one becomes 1 over n plus 1 over sxx sigma square. And here this one becomes n times sxx sxx plus n sigma square, and sxx is sum of xi minus x bar let me see. Oh, I see. Here we have x bar square here, and so here we have yeah, x bar square here. Okay, and so this is x bar square, and so sxx is this thing, and this part is sum of xi squared minus nx bar squared, and here we have plus nx bar squared, so this part cancels, and so this thing becomes sum of xi squared divided by nsxx and sigma square. Okay, so this derivation gives this thing. So this is proof for variance of beta 0 hat. The next derivation is covariance of beta 0 hat and beta 1 hat. And here we know that beta 0 hat is y bar minus beta 1 hat x bar, and also beta 1 hat is sxx and sum of xi minus x bar times yi. Okay, this is what we know, and let us define beta 0 with the form of yi's, and so to do that, this is beta 0 is sum of yi's over n minus sxx sum of xi minus x bar times x bar times yi. So here we will move yi. So sum of I equals 1 to n. Yeah, so we can represent this thing like this. Okay, and why we are doing it? Because to calculate covariance of beta 0 hat and beta 1 hat, we can re-express this thing as covariance of sum of I equals 1 to n 1 over n minus sxx xi minus x bar times x bar times yi, and comma, and this part is sum of I equals 1 to n sxx xi minus x bar times yi. Okay, we can re-express this way, and what's next? So this can be expressed as sum of I equals 1 to n and j is equal to 1 to n, and covariance of 1 over n minus sxx here and xi minus x bar times x bar yi, comma, this times yi, comma, and sxx sum of xi minus x bar times yj. Okay, and here again, if I and j are equal, then covariance of yi, yj, this is variance of yi, which is sigma square, and if I is not equal to j, then covariance of yi and yj is 0. So this form can be simplified as I is equal to 1 to n if I and j are equivalent. So this case, the covariance of if they are yi and yj are the same, then this one is 1 over n minus sxx xi minus x bar times x bar, and this thing as xx times sum of xi minus x bar, and times variance of yi, which is sigma square. And if we calculate this thing, oh, actually, we don't have this one. Oh, yeah, okay. So we don't have this one, and so this thing becomes n times sxx sum of xi minus x bar minus sxx squared and sum of xi minus x bar squared x bar and times sigma square. And here, actually, this part, sum of xi minus x bar, this part is 0. So this part goes away. And here, this part is sxx. So this can be 1 of sx square cancelled. So now this one becomes sxx here, and this part is x bar actually this is minus, so minus is here, and sigma square. Okay, so so we prove that the covariance of beta 0 hat and beta 1 hat is this thing. Okay. Before we move on to example problem, I'd like to tackle some properties using matrices. So this slide is taken from chapter 11.10, and actually in chapter 11.10 there are not rigorous mathematical proofs for it, but I think these kind of properties will be covered from linear model class or what is it, multivariate statistics class. So that will be it will be covered from that class. But the simple proof for this is that you may need to know that variance of so C is matrix and y is random variable. Then the variance of Cy is C variance of y and C prime. Let's see whether this is correct. K by 1, M by K. So variance of y is K by K. C is M by K, and C prime is K by M. Okay, so the resulting matrix is M by M variance matrix. And so let's check what it is. So beta hat is X transpose X inverse X transpose Y, and expected value of y equals x beta. So expected value of beta hat is expected value of x transpose x inverse X transpose Y. And here the random variable is Y, and if expected value of Cy, it is C, and expected value of Y. So this is random, and the C is constant matrix. So in this case, we have these two properties. Let's say we have these two properties, and then this one can be written as X transpose X inverse X transpose expected value of Y. And actually, since Y is X beta plus epsilon, expected value of Y is X beta. So we can put X beta here, X beta here. And what we can see is that X transpose X inverse X transpose X beta, and this one and this one, some matrix transpose matrix, this is identical matrix, so this becomes beta. So we can check that, we can check the first condition, the unbiasedness. And what about the second part? Variance of beta hat is variance of X transpose X inverse X transpose Y, and this is C is here X transpose X inverse X transpose variance of Y, and C prime is X transpose X inverse. Okay, and the variance of Y, because the Y is this thing, variance of Y is actually variance of epsilon. Variance of Y is variance of epsilon, and this is I sigma square. Okay, and so this is I sigma square, and this is X transpose X inverse X transpose X transpose X inverse and sigma square. And this is, since one of these cancelled, the variance is X transpose X inverse sigma square. Okay, so this is variance of beta hat, and so variance of beta I hat is diagonal component of this thing. So this matrix is X transpose X inverse matrix, and the diagonal component of this thing is variance of beta I hat, and the covariance of beta ith and jth. So here we have ith, and let's say we have jth, and I and jth component of this is covariance of beta ith and beta jth. So we proved for this thing, and actually if you admit this property, we can simply prove these properties. And I will not explain more firmly about these two properties, and I think that these two properties will be covered the multivariate statistics class or linear model class. Okay. Now let's move on to example 11.2. Find the variances of the estimators beta 0 and beta 1 hat for example 11.1. And so previously we derived that the variance of beta 1 hat is this thing, variance of beta 0 hat is this thing. So you can use this formula to find the variances. Firstly you put the put values for xi and yi, and n is 5, and next you can calculate sxx and sxy. Actually you don't need to calculate sxy, but anyway you calculate sxx here, and as a result 1 over sxx, so it is 0.1. So variance of beta 1 hat is 0.1 sigma square, and variance of beta 0 hat is this one, so 0.2 sigma square. And also you can derive the same thing different way. So beta hat um, is variance of beta hat is x transpose x inverse sigma square. So you can find this matrix directly. So if you use this matrix form, you can firstly write your x matrix this way, and then you can calculate this one. So x transpose x inverse, you can calculate x transpose x inverse, and that's this one. So what you get is 0.2, 0, 0, 0.1 sigma square. So from this result, you can check that variance of beta 0 hat is 0.2 sigma square, and variance of beta 1 hat is 0.1 sigma square, which is same as the one we derived using this formula. And also you can also check the covariance of beta 0 hat and beta 1 hat is 0. Okay, so yeah, I solved this one with two ways, and if you come to know this matrix form, then you will. It is much more easier to calculate this way. So that's why I'm explaining both methods together. Okay. Okay, so far we learned about linear models. Actually, from the book, it mainly talks about simple linear regression situation, but I think that the matrix version is more general and easier to understand and calculate. So I'm explaining both together. So I'm explaining chapter 11.3 or 4 3 with 11.10 together, and so I hope that this will help you understand the concept easier. Okay, and see you next week. Thank you.